Hi, everyone, and welcome to the Sequencing and Preconfirmations call number 11. Today we have folks from Coinbase who will be talking about Keyspace. I think we have a presentation specifically by Niran. But before that, I kind of want to talk about ETHCC. There is a persistent testnet that is being spun up. So this is a public and persistent testnet called Helger. The idea is to basically continue on the success of Zuberlin and go from a DevNet to a testnet. Is not, I think most of the focus is not on the Holesky testnet. By having our own private testnet, we'll be able to move a little bit faster. The name Helga comes from Dutch. It means bright because the future is bright because of base rollups. And as far as I can tell, there is a lot of interest from many different teams, 20 or so teams across the whole stack. So if you are interested in participating or getting involved in this persistent testnet, do get in touch. Without further ado, Niran, the floor is yours to talk about Keyspace.
All right. Thanks, Justin. Thanks, everybody, for being here. I'm calling in from, I don't normally live in California, but I'm in California right now, and that's very early. But hopefully that does not affect the quality of the presentation. So let me start my slides. As I'm going through this is fairly informal, so feel free to chime in, and if it gets too much, I'll push back on it. But let's start by assuming that it's going to be totally fine. So my name is Niran Babalola. I work on the base team at Coinbase. Our goal in general is we want as many people on chain as possible. So that means as many users, that means as many builders as possible, that means as much value as possible, and that means that we have to scale the network so that can all happen cheaply for all these users. So that's what we believe, that's what we're working on. Part of that vision is making sure that people can use smart wallets across all the chains that they use. So for us, this isn't just a base thing. We expect that for people to have the kind of user experience that we want to have, that they're going to need smart wallets to have paymasters, to have passkey signatures for their accounts, all the benefits of that. But they need that to be a unified experience no matter where they go. If they go to another chain and they have a bad experience, that means they're having a bad experience on base too. We don't want that. So the what where Keyspace fits in is that it's a cross-chain key store for these smart wallets. Vitalik has done a lot of writing about this vision of having a single source of truth for the signing keys of your wallet. Because once you move away from externally owned accounts to smart wallets, the smart wallet is storing the signing key that controls the wallet in the storage of the account. If you're on another chain, you don't have that storage. Everything gets out of sync. So there's a lot in the Keyspace docs. There's a lot of writing in the references that I've linked to. So feel free to, if you haven't seen all that writing that Vitalik has done, there's a lot of links there. It's all good stuff. So we're trying to implement a version of that vision. Keyspace is implemented as a ZK rollup. So we settle to Ethereum, the state root stored there, and every time we're trying to update the root, there's a zero knowledge proof that's being verified to update the root each time. This is not a ZK EVM. It's not a general purpose blockchain at all. And in that sense, it feels weird to even think of it as an independent blockchain. When I think of an independent blockchain, I think of Optimism. I think of Arbitrum. I think of Gnosis Chain. I think of these things that have their own rich state that people are querying, that people are sending transactions with, etc. In my head, what Keyspace is doing feels more like a fancy smart contract. It's one application with very limited operations that you can take on it, like a smart contract would be, but it is its own independent chain. We limit the operations that can happen on Keyspace because at the end of the day, this chain is controlling access to your funds. if there's some sort of bug, some sort of error, because we're trying to support all the use cases in the world, that ends up cascading to people's wallets and people have a bad time. So instead, we want to minimize the attack surface of key space. So there's very few operations that can happen. We want it to be straightforward for people to audit, for people to trust, and for it to be reliable over time. So that's what Keyspace is. It's a minimal key store rollup. It's a ZK rollup, few defined operations, and that's what's going on here. So, in the context of this call, I haven't actually been to any of these presentations, but my understanding is that it's a lot of roll-up builders thinking heavily about pre-confirmations and things like that. So, in that context, the limited statefulness in key space kind of informs like what we've been thinking that we need to care about, and we're very interested in feedback from you all who've done a lot of thinking about this. But to think about where key space fits in Ethereum, we have this rich account-based state where the order of all transactions is affecting what happens on chain. It's rich statefulness. It's why Ethereum is this very useful platform for writing these applications. If you go a step down, you have Bitcoin's UTXO-based state, where the order of the transactions that are consuming the same UTXOs is very important. But other than that, if I'm using some UTXOs and you're using some UTXOs, our state is independent. So the ordering of those is less important than it would be in Ethereum. And then taking a step even lower than that is something like certificate transparency. If you've heard of it, great. If you haven't, it's not that important. But it's basically the state doesn't depend on the ordering at all. It's just a log of the certificates that have been issued. So the ordering isn't super important. Keyspace is kind of in between Bitcoin and certificate transparency on the spectrum. Every wallet has its own record, and each record has its own independent history. So you can manage your keys, I can be managing my keys, and the fact that our transactions might be included in a different order isn't super important. And it's for this reason that we haven't been super focused on things like pre-confirmations, things like that. We don't think that we need to think about that. If you think differently, we want to know so we can correct that. But that's how we view statefulness in key space. In terms of how key space is sequenced, right now the deployed testnet version is it's permissionlessly sequenced by anybody who wants to show up and advance the state of the rollup. There's no that you don't get a slot to prove or anything. It's just you show up and you prove. This is not shippable in its current state. It's just the way things are right now. In particular, the current model introduces a lot of contention. If I start proving a block and you start proving a block, we're going to have a bad time because when your proof gets on chain, all the work that I've done is now invalid. And sometimes that work is very computationally heavy to get proving times of currently about 5 to 10 minutes with our current circuits. We are running a relatively beefy machine, costs money to do, and we don't want that sort of contention to be there in real life. So the end game for sequencing in key space, we believe, is base sequencing. We want to inherit a lot of the benefits that you get from relying on the L1 sequencers to do the sequencing. So in terms of liveness, right now, if our sequencer stopped, it's very hard for somebody else to step in. If we had a whitelist sort of approach, you could benefit from having a couple of other people, but we really want any L1 validator to be able to step in. We also want to benefit from the decentralization of the validator set, having any instead of trying to build our own validator set using Ethereum's, knowing that the allocation of proving the sequencing slots is already well distributed. And then we definitely want Ethereum alignment because again, we're not trying to create our own ecosystem. What we want to end up with is something that the entire Ethereum ecosystem sees as core infrastructure. We want many users' wallets to be integrating with this system. Does somebody have a question? If not,
George, maybe I'll just mute you if you don't have a question.
no worries. So the model of base sequencing that is kind of the latest thinking that we're familiar with is the vanilla base sequencing, where basically if the current L1 validator is opted into the system, then they're the validator for our chain, and if they're not opted in, then a random opted in validator would be selected. That's kind of the setup that we expect to end up with. So, getting more into how Keyspace works, there's basically a sequencer running that's accepting users' key change requests through RPC calls. When you want to change your keys, you say, "Hey, Keyspace node, here's my signed key change transaction. Can you include it for me?" The sequencer then takes a batch of key change requests and creates a recursive batch proof for all those requests. It submits those proofs on chain to advance the state root that currently costs 330,000 gas with our implementation. My understanding is that the lower bound for these types of proofs is 200,000 gas. So there's some wiggle room, but we can't get it down by like an order of magnitude. It's kind of just the cost of doing business with ZK rollups on Ethereum right now. Definitely looking for input there. And then there's also a forced inclusion path for to avoid censorship by the sequencer. You can submit your recovery directly on L1, and then the sequencer is forced to include your recovery in an upcoming batch. So the way the force inclusion mechanism works right now is that for every one off-chain transaction that the sequencer wants to approve, basically something that they receive through an RPC call, they have to include one of the forced inclusion transactions alongside it. So when you submit your forced inclusion transaction, you're not guaranteed any sort of ordering. You're just guaranteed ordering within the set of forced inclusion transactions. The sequencer will be picking one of each and going from there to create its batches. So you'll be eventually included in the state of keyspace. So once we have the updated keyspace root on L1, where we really want this is L2. Most of the smart wallet activity we expect to happen on L2. You can have a smart wallet on L1. You can read the keyspace state root from L1, but where the action really is L2. So we need to get these key store roots onto L2. And the way that we do this currently differs depending on what kind of chain we're syncing to. For OP stack chains, the L1 block hash is available from one of the built-in contracts. So we can do Merkle proofs from that L1 block hash to be able to sync the key store state root to a contract on the L2 that wallets can access. For other chains that don't have the L1 block hash, we need to rely on an oracle. For our current proof of concept, we're syncing to, I believe, 7 chains, and then the 8th chain is Ethereum mainnet. Uh, the 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 way that we get to most of these chains is using Wormhole as an oracle. At the end of the day, we don't want to necessarily rely on a single oracle. We're investigating things like Hashi that can produce consensus among oracles for the L1 block hash and then prove from there. But the current deployed system from the latest release from this week uses Wormhole to sync the key space root directly. So there's no intermediary of the L1 block hash that's being synced. Since we're using an oracle, we're just saying, just get me the key space state root and get it to the chain that I care about. So that's how we get to most of the chains right now. So there's those 2 trustless chains right now, which are Base and Optimism, and of our supported chains, that the OP stack chains, and then the rest are Oracle-based chains. Arbitrum is an L2, so it could theoretically have the L1 block hash that contracts could access, but there's currently no way to actually access that L1 block hash on Arbitrum that we know about. So if we're wrong about that, we want to know. And if we can get that L1 block hash, we definitely want to have it. The other way of generating these proofs would be, instead of using the L1 block hash, to use the EIP 4788 beacon root proofs. We've implemented this, but currently I don't think we're actually going to end up using this anywhere. The like for the chains that are actually rollups, they tend to either implement the L1 block hash or nothing at all. So Arbitrum, for instance, doesn't provide the L1 block hash, but they also didn't implement EIP 4788. Their approach was to basically make the beacon root oracle, I think, revert, if you try to call it, because we're like, we don't have a beacon chain, so this shouldn't return anything. OP Stack does support beacon roots, but since we have the L1 block hash already, we're just using that to prove that. So we expect that that mechanism won't be used, but it's an avenue if for some reason people prefer implementing that to the L1 block hash oracle. The other benefit of the beacon root oracle is that the standard specifies the address that the oracle should be reading from, and the addresses kind of have cascading effects on addresses throughout the system. If I have to refer to a particular address on one chain and a particular address on another chain, then my ability to use create to generate these contracts is limited. I'm going to have to use something else to get the consistent addresses. But with the beacon root oracle, we could actually deploy it using create and that would be nice. But we don't think that's going to happen. Lastly, the deposit transactions are the most straightforward way to do this for rollups, but they're just very expensive right now. But I think 10 times more expensive than doing Merkle proofs. So Merkle proofs it is. So once we have the key space root on the L2 chains, the all L1s, everybody knows what the latest root of key space is. The next thing is for wallets to actually integrate with Keyspace. And the way this integration works is if you think about the way you have signing keys in your smart wallets today, it's you just store it directly in the contract storage. So when you're integrating Keyspace, you basically remove that. Your signing keys no longer live in your smart contract; they live in Keyspace. So if your signing keys aren't there locally, that means that with every transaction you send, every single one, you need to prove that the signing key that you're signing with can actually access the wallet. So instead of just providing a signature of the transaction that you're trying to send, you provide a signature. You provide the data that's stored in Keyspace for your record, which in this case is the public key. And then you provide a proof of your configuration in Keyspace. This proof is a snark right now, but it's equivalent to a Merkle proof of the state in Keyspace. There's nothing fancy going on there. It's just cheaper to verify the snark than it is to verify a Merkle proof. And actually, that may be incorrect. Let me back up there. By using snarks for the keys for the state proof when you're sending a transaction with your wallet, that gives us the ability to aggregate those proofs later on. Currently, there's no aggregation happening, but if we built a ERC 4337 aggregator, we could aggregate those proofs, so which would lower the overhead for these transactions. So once you're providing all this data, you do your normal signature verification, but on top of that, you also need to verify the snark that's saying that, hey, this key that I'm using is actually in the latest state of Keyspace for my wallet. And with those two things together, your transaction is authorized. So if that's happening on the smart contract side, on the client side in your JavaScript library and your mobile app or whatever you're doing, in addition to just signing the transactions the way that you usually do, you also need to be fetching that state proof from a Keyspace node when you're in the process of signing a transaction, making sure that you have the latest proof to be able to send with your transaction to authorize that signature. So that's how the wallets are integrated. There's also work that bundlers can do to make Keyspace work better. So one is to support those ERC 4337 aggregators that I was talking about. Those state proofs that we're including with each transaction at current prices an overhead of about 11 cents for each transaction. That's much higher than our goal. We want transaction to happen in 1 second and for them to cost 1 cent. And if we have an 11 cent overhead for these transactions, that's not where we want to end up. We want to get it much lower than that. So aggregation is one path towards lowering that overhead. And then another thing that bundlers can do for us is to allow our state lookup across contracts. So when we provide that state proof with each transaction, and we're generating and we're verifying the proof, we need to access the latest key store root value. That value lives in another contract, and the ERC 4337 standard does not allow that in the process of validating transactions, and it does this to protect the bundler from losing value. However, the bundlers that we've spoken to are very aware that that constraint is too strict. So basically, making sure that there are possibilities to work around that by configuring the like your bundler instance to say, hey, these specific state accesses we know about, just allow them. The standard doesn't allow them, but we've looked at them and just let it go. That's one path for allowing this. The other is to create kind of a standard singleton contract for these cross contract accesses. And what would be special about the singleton contract is that the bundler's issue is that they don't know when the state is going to change in this contract that you're doing this access to. So if you have a singleton contract where each storage slot has a kind of frequency that is enforced by the contract, that you try to update it and it just doesn't allow it because you updated it too recently, then the bundlers can say, hey, we trust accesses to this contract. You don't have to tell us about it. You don't have to get each one of us to configure this because we know this contract enforces the constraints that we need to be able to protect our resources. That's another path forward. So either per application configuration, we hope that people value Keyspace enough to be able to do that, and just a general solution for all applications that want to be able to do cross contract accesses in their smart wallets is another path forward. Lastly, there's work that rollups can do to make it easier to integrate with Keyspace. We're already deploying to rollups, deploying to all L1s, but the cost and the experience can be better if rollups were doing more to support our use case. So one thing is just support reading data directly from L1. If we're doing that, then we wouldn't have to do all the syncing work to get the route from L1 to all the other chains. And if you're a rollup, you have that L1 node right there. Why won't you let me read from it? It would be so convenient if you just let me read from that L1 node that you have on your machine. So there's various proposals out there to make progress on this, but my understanding is that nothing really has legs yet. The Scroll has their own implementation that they've already gone and rolled out, and that makes their implementation of a key store much more convenient because they can just read L1. There's an OP stack proposal that seems to be stale now, but they basically had like a remote static call opcode that would be very useful. But we would like to read from L1. That would be very nice. Another thing that they could do, and this is very much a wish list. I don't know how convincing I can be on this front, but if rollups, if all the L2s, all the L1s, if they just decide that key space is so important that they want to make key space part of their consensus, that would be great. Then you could just read directly from Keyspace. I don't have to do my state proof of like, oh, this is the key that controls my wallet right now. Just read from Keyspace and say, oh, okay, here's my opcode that lets me read from Keyspace and says that that I'm allowed to do this. That would be really great. I don't expect that to happen, but if y'all are excited about it, I want that. That would be good. So in terms of our roadmap, where we're going from here. So we have this testnet beta that's on the 8 chains that I mentioned. It's in a state where it works, and we just need to make it better in terms of speed, in terms of cost, in terms of operational efficiencies, and in terms of security. So that's really where we're headed. The kind of the top line issue right now is optimizing our recursive circuits because that has cascading effects to the whole system. If we change the proving systems that we're using, that's basically rewriting all the circuits involved, and that's kind of a big impact. So we want to take on that cost earlier rather than later. There's various systems that have pitched that they have 30x, 100x speed improvements in terms of proving time over what we're currently using, which is kind of the first generation of Planck proofs. So we could try using Plonky 2 and see if that gets us the speed up that we want. We could try using Plonky 3, which currently it seems like there's a lot of momentum behind. In particular, if we end up using Plonky 3, then we can benefit from using something like the SP1 ZKVM. So when people want to write their own custom contracts with their custom wallets with their custom recovery logic, we're going to provide our own circuits with general recovery logic out of the gate. So if you have like a Emoven multi-signature wallet, you're probably not going to have to write your own circuits. But if you have some sort of fancy wallet that you want to implement, you do currently have to write your own circuit to get that implemented. It would be great if instead of saying, hey, write some domain specific circuits to get your logic written, if we could say, write some Rust or write some general purpose language, have it compile to using a ZK VM and just plug in to our verification systems. That would be great. So that's one benefit that we see from that. Like we're not necessarily right now at the cutting edge of like knowing what the latest going on in the ZK ecosystem is. So again, if Plonky 3 and SP1 sounds like, oh, there's actually another approach that you should be taking, looking for input there. But right now, we're excited about trying out Plonky 3 and seeing where that gets us. Instead of having 5 to 10 minute proving times, I hope it gets down to seconds, and that would be pretty cool. Another thing we want to do is the ERC4337 aggregation that I mentioned before. We also want to think about making key space in L3. So what that means is I was talking about how the lower bound of our batch proof is 200,000 gas. And right now, the actual cost is 330,000 gas. That ends up being, at current prices, $8 to $20 for a batch proof to settle on Ethereum's mainnet. That's a problem for our application. Like if you're, let's say you're a ZK EVM, hopefully you have enough transactions happening in your system that you can kind of spread that cost out among all the users, and it doesn't end up being that big of a deal. We are a minimal ZK rollup for changing keys. People don't change their keys that often. So our low utilization ends up making that cost of proof validation a big deal. Uh, in the early days, it's very unlikely that we'll be able to batch any recoveries together. Like if a recovery is happening, the chance that somebody else is changing their key at the same time, very low. Are we going to tell people that when you want to change your key, it's going to change once per day, and we're going to batch up the 10 recoveries we have each day to get the cost down? That's probably not the greatest story. So instead, what we expect to happen is to get that proof validation cost off of L1 and to have it on an L2 instead, using some sort of a special purpose L2 that's for aggregating proofs. So when I say it's an L3, it's not that it's settling on base or settling on some other general purpose L2. It's really thinking more like something like Polygon's Ag layer. I think Avail has a proof aggregation system. I think in the Starkware ecosystem, they have their own kind of proof aggregation system. That's the kind of L2 that I'm talking about, where again we're seeking a minimal attack surface, so minimal functionality, but really we're just seeking something that aggregates the proofs so we can settle to L1 and share with everybody else that happens to be trying to settle their proofs to L1 at the same time, rather than taking that cost on ourselves. So that takes the cost down significantly. I think Vitalik was writing an estimate that's basically like the cost of a storage plus some bookkeeping operations, so something like 8,000 or 13,000 gas. I forgot exactly what the estimate was, but it's a far cry from 330,000 gas, and that would make it much more feasible to have even potentially users cover the costs of their own recoveries. Right now in the testnet version, it's just we're running the thing. If we were launching key spaces in L2, we'd probably try to find some way to cover that cost because it doesn't make sense for users to pay $8 to $20 to change the keys. So trying to get to a path where we can, even if we launch with an L2, where we have a roadmap to get to an L3, where those costs no longer need to be subsidized at that large of a scale. Speaking of subsidies, we also want to be able to collect user fees from recovery transactions. And when I say collect user fees, I'm not saying we want to be rich. We want to make money from users changing their keys. What I'm saying is that we want Keyspace to be more resilient than it is today. Right now, the operation depends on the generosity of Coinbase Incorporated. We run the thing. The costs are covered by the we're running a sequencer. It's the keys are going to get processed. But for Keyspace to be the kind of ecosystem-wide infrastructure that we want it to be, it cannot depend on generosity. It has to depend on economic guarantees instead. So the current thinking around making sure that there's a way for users to pay for recoveries, or for their wallet provider to pay for their recoveries for them, is to allow intents to be used to trigger recoveries rather than just directly sending your recovery to the Keyspace node. What that means is making sure that there's a way for the sequencer to prove that they've included a particular user's recovery transaction. So then they can go to whichever chain that the user initiated their intent on and claim the value that they want to be compensated with for processing that recovery. In that model, we could continue subsidizing it. Like if Coinbase is running the sequencer and we say, hey, we support these intents, but like we're just covering it for now. So we don't care if you actually funded an intent or not. We could keep doing that. But then on the day when Coinbase decides we're not so generous anymore, we're not subsidizing this anymore. Anybody else could step in and say, okay, I'm going to run a sequencer, but instead of doing what they were doing and just accepting any recovery, I'm only going to accept recoveries with a funded intent, and then I'm going to collect that money at the end of the day. That's the kind of workflow that we want to support, so the system can be more resilient and not dependent on subsidies anymore, even if it is subsidized. Lastly, we want to be able to support time delayed recoveries. So, one very common pattern in terms of securing crypto systems is just time delays. If something goes wrong, if you have the time to take action to like mm, reject whatever was happening, that makes systems easier to trust, easier to reason about. And right now, there's no mechanism to have time delays within Keyspace. So let's say you actually lost your key. It's not like, oh, I'm changing my key. I have this one pass key. I want to approve another one. But man, I lost my key. I don't have it anymore. It would be nice to be able to have some sort of guardian feature where there's somebody else who can help you recover your key. But right now, in the current implementation of Keyspace, there's no distinction between different recovery methods. If I'm adding a guardian, they have as much rights as I do to my wallet. They have control to all my funds, and I probably don't want that. So time delayed recoveries allow us to add basically another type of recovery where when you initiate it, there's some sort of configurable waiting period. And then after that waiting period is passed, that's when the key change is processed. So that ends up being a significant change to the circuits because right now when you're the account circuit, which is what's used to prove the key changes, the inputs that it takes are just user provided inputs. There's no kind of environment provided inputs to the circuit, and that's what we would need to be able to implement this kind of prepare and commit two-stage process for time delayed recoveries. So the easiest thing to reason about is, let's say you were initiating your time delayed recoveries on L1, then we need some way to get the L1 data into the circuit and prove their. I'm assuming that that path is relatively straightforward. That if we wanted to allow the recoveries to be initiated on L1, doing the proof in circuit from the L1 block hash might make that possible. Where it gets harder is if we want to say, okay, it's expensive to initiate the recoveries on L1, so maybe we want the Guardian to be able to initiate the recoveries on an L2. What does that look like? Well, if it's an optimistic L2, the settlement times are fairly long, but maybe those settlement times are actually not an issue in our time delay. If our time delay is 1 week or 2 weeks, then the fact that it takes a week to settle, maybe we don't care. And we just end up doing proofs against an L2 in that way. But also want to investigate the ZK L2s and doing time delayed recovery proofs from those chains as well. So that's kind of an overview of where we're heading. We're always looking for feedback. In terms of like zero knowledge systems, we've learned so much from the people who've been doing cutting edge work. There's always more to learn there. So looking for feedback on that. Roll up architecture. Lots of people have been thinking about how to make this happen well. We're looking for feedback there. And if you've just been thinking about wallets for a long time and you have a case that you want to throw our way, we're always interested in talking, and we want this to be a neutral piece of infrastructure for the whole Ethereum ecosystem to rely on. And at the end of the day, we want millions of users using smart wallets to send their transactions that cost 1 cent, that take 1 second to process, so we can build an economy on top of these decentralized systems that empower people. That's Keyspace.
Amazing. Thank you so much, Niran, for this extremely thorough and comprehensive presentation. We have about 20 minutes for questions during the public part of the call. Anyone want to kick us off on the questions? Lynn, go ahead.
So yeah, thanks for the talk. I have a question about, so you mentioned that you probably, or you don't need pre-confirmations, but you also mentioned that you're going to use like the vanilla-based sequencing, which is actually a pre-confirmation solution because so where they require the L1 proposer to explicitly opt in, and opting in is required because they need to be like subject to slashing condition, and the slashing condition is required because you need like flashing when they equivocate on the pre-confirmation. So I was wondering like why you need that kind of explicit opt-in. Like, is it going to be used for something else than pre-confirmations?
That's a great question. So the answer is I don't know what I don't know. So the thing that seems attractive about vanilla-based sequencing is really kind of the smoother adoption curve. The fact that like the uh, we want to kind of leverage the distribution of proving slots that the L1 logic already provides for us. So the opt-in is really, in the thinking so far, is just a way to like when the nice the kind of the happy path for distributing these proving slots is literally for every L1 sequencer to be running keyspace, or for many L1 sequencers to be running keyspace, because then we know that many people are involved in proving for keyspace, and the chances of liveness failures because there were like few people actually involved doing it and then they decide to stop is reduced. So really, that's what we're looking for in the approach. If there's a simpler way than vanilla-based sequencing, if the opt-in isn't actually necessary, that's definitely something we want to think about. But the way I think about the opt-in right now, it's just we're trying to know who to select from in both the happy case, where the current L1 sequencer is saying, hey, I want to participate in the system, or in the unhappy case where it's like the current L1 sequencer knows nothing about keyspace. Who do we pick now? Should be one of the people who've opted in. But if there's another way to do it, and I suspect that there might be, very interested in that.
I see. So it's kind of like to get the liveness guarantee from having explicit opted in entities.
And that's what we're looking
Yeah,
for
okay.
there.
I see. Yeah, thanks.
And once you have user fees, then I guess the searchers will be interested in providing bundles to the builders, and you'll get this for free with PBS. But one of the things you want to make sure of is that you don't have this contention with different people building proofs that are inconsistent with each other. But if you can get the proving time to be under 12 seconds, which might actually be possible in your case because you have a very simple virtual machine, then this is the best case scenario where you don't need any opting in.
That would be great if the proofs were that fast. There's a question in the chat. Is proving and sequencing permissionless? It currently is in what we've deployed right now. There are kind of two paths towards a broader launch. One is just biting the bullet and doing base sequencing and having the first production release of key space using that method. And then it would continue to be permissionless, and we would just be relying on the L1 sequencer distribution to make that happen. There's another path towards release where we say, okay, that work is going to take too much time, but we want to get this out there. Let's just launch the way that most rollups launch and have a whitelist of allowed sequencers and launch them that way. So that's the scenario where it doesn't end up being permissionless, but that's not our end goal.
Sorry, that was just my question, but thanks. That was a great talk. I really enjoyed that and the way you explained yourself. How would you weigh up like the odds of like path 1 versus path 2 right now in your head? Like path 1 being going based and path 2 having this whitelist, and do you have an intuition for that? Or
I think there's a decent chance that we end up actually implementing base sequencing. That depends on. Ideally, we're not we're not super early in doing that. But especially if there are live implementations out there, I expect that we would follow quickly with our own implementation and launch in that way. But we just haven't done enough research to know how big of a commitment implementing that would end up being. If it ends up being very large, I can see us launching just. It seems fairly typical to kind of kick the can on that particular issue with rollups and say we're just going to gradually decentralize it. So if I had to say which one is more likely, I would probably say gradually decentralizing it, but it would be better than that.
okay, thank you.
I have a question. I have a question about the latency. So for the various key store rollup operations, what are the latency requirements in your mind? I think this is related to what kind of sequencing model you end up choosing. And if you are using proof aggregation, then because we are working on proof aggregation, we want to understand what's a requirement on the latency side when people are doing these like a ZK operations, if that makes sense.
Yeah, that makes sense. So for our use case, changing keys, it's typically not super time sensitive because of the requirements for changing the key. You have to have access to the old key. You're signing the new key. Like you want to be able to use the new key. It would be nice, but since the wallet has access to both keys at the same time, if it's slow to update, you just keep signing transactions with the old key until the update happens. So we don't have if it took 2 hours for a key to update, I think it would be fine. I think we have kind of like a constraint that we put in one of the design documents that might be less than that. But if your keys change in 30 minutes, I think we're good.
Thanks.
One question I have is around governance and how updates to the contract are done. Ideally, we have a super simple virtual machine and it's fully immutable. But do you think it's more likely than not that there will be governance initially, and what would that look like?
So the current thinking is no governance at all. So basically deploying key space as an immutable system. And when an upgrade needs to happen, you deploy a new key space. The lever for upgrades in that scenario would be on the wallet side rather than on the key space side. When you want to update to the latest version of Keyspace, You update your smart contract wallet, that wallet is pointing to a different key store and using different logic than your initial wallet was. So because the wallets themselves are typically upgradable, we believe that key space probably does not need to be, and it's probably better if it's not. So then people can opt into whatever version they want to use.
Amazing. So a very similar model, I guess, to Uniswap, where you have V1, V2, V3 potentially.
Exactly like that.
Approve.
Hello. So I have two questions actually. The first one was based on what you just recently answered. So regarding the part where you said, like if you have access to both keys and even if it takes like 30 minutes to update, it's fine. So my first question is, like obviously this, if you lose, I was thinking of this scenario, like let's suppose you lose a key, right? For any XYZ reason, maybe you realized you pushed it on GitHub by mistake, or you did something, and like similar to the Web2 world, you lose an API key. So you can instantly go revoke it. Now, this doesn't exist in the EOA world, but do you think like smart contracts would like to provide this feature? Like by any chance, if you leak your private key, you can instantly revoke it? Because if that's true, then a 30-minute or a 2-hour upgrade might be like very late for something like that.
So you're absolutely correct there. The in terms of thinking of the engineering behind this, it's kind of easy to take the lazy approach and be like, the current systems do not provide this, so do the new systems necessarily need to provide this? The at least for the first iterations of this kind of system, it's much easier to approach it in a way that where latency is acceptable, because the existing EOAs just don't provide this at all. In the main scenarios of key changes, like the fact that smart wallets allow you to change your keys, it it's I guess maybe some people are implementing it as kind of like a disaster recovery sort of thing. Oh, I exposed my key, let me change it. But the primary use case that I've seen for it is just letting you move to a different device or move to a different signing key rather than the fact that you've exposed it. Since exposing a key is a catastrophic thing today, expecting it to continue to be catastrophic is the way that we're currently thinking about it. Don't expose your key. That's bad. The key space can, like, just technically speaking, can help people respond to that. I publish my key on GitHub. Let me change my key as fast as I can. Like, it's possible to design a system that does that. It's just in my head so far down the list on things that wallets need from us that it hasn't been a priority to design for them.
Makes sense. Thank you. And my second question was around, I think in the Arbitrum side, you mentioned that you have to use an oracle because you don't have the block hashes. So maybe I'm missing something, but is it possible that, like you deploy a contract on L1 and you send the previous block hashes by like L1, L2 messaging or some other way?
Yeah, so we could implement a trustless deployment of key space on Arbitrum through deposit transactions. The only reason that we don't is because the deposit transactions are expensive. But I honestly hadn't thought of it deeply until you just mentioned it. So it really depends which which factor ends up being more important to people. If people are like, hey, we want trustless deployments of key space in as many places as possible, then we would just fall back to deposit transactions on Arbitrum and achieve trustlessness that way. If the costs are more important, then since we don't have a cheap trustless way to do it on Arbitrum, we would stick with the Oracle. But that's a very good point to bring up. We could just use deposit transactions.
Makes sense. Thank you.
One question I have is, what is the team size of the key space project?
So right now it's about 3 people. I think we have one more person who's about to join the team. But the just so I'm not taking credit for somebody else's work, this work has been led by Michael DeHoog, who's done a lot of thinking about the key store rollup. really kind of wanted to be like a torchbearer for, like, Vitalik did all this writing. It's like, hey, like, somebody needs to go and implement this, and making sure that it gets implemented in a way that the ecosystem can rely on. So Michael's done a lot of thinking on that. I joined the base team in like late January, early February. So I haven't actually been around that long, although maybe I need to stop saying that because the months are passing pretty quickly. But I've enjoyed, like, it's been a very fun project to work on. I've been in like the crypto space for a while, and most of the projects that I work on, having real people use them and get value from them, it's hard to get to that point. But working on something like Keyspace, where it can like be a core piece of infrastructure for the ecosystem, has been a relative delight in that fact, because I can like the other wallet teams, like interacting with them, getting to know like their concerns, because they actually want real users to be impacted by these systems. It's been a fun ride.
And if there's no more questions, I'll keep asking. You mentioned that you wanted to potentially do a fast follow in terms of launching a base rollup. Do you have an ideal timeline in mind as to when you'd like to launch?
So we're currently on a cadence of roughly quarterly launches. So really getting as much out as we can each quarter is the idea. For the next release, I expect that sequencing isn't actually going to be super high on the list, because we're going to be doing all this work trying to evaluate Plunky 3, all this work on. There's another thing that was super. I forgot what our second priority was, but the currently there's higher priorities than the sequencing. So I expect that might get punted down a little bit. So if we were launching a base rollup, I would currently guess that would be early next year.
Understood. Thank you. Any final questions before we wrap up the public part of the call? Or maybe Niran, if you have questions for this group, we could also entertain them.
Yeah, the main things that we're always looking for is feedback on like base sequencing in general. We've been following the discussion from afar, so when our assumptions sound like they might be off, like thinking of yourselves as the experts rather than us and giving us the feedback, definitely interested there. And like just in terms of choosing like ZK stacks and things like that, the experiences that people have had, that's always welcome as well. Justin, thanks for all the information you provided for us so far. That's been very helpful, and always interested in more feedback.
Lynn.
Okay, so I have a more nerdy question about the based preconfirmation sequencing side. So, and it might be more for George, but like, so in the vanilla based sequencing, so like you randomly elect for a non-opted in slot, or when the proposer is not opted in, you randomly select like a validator who has opted in. But the problem here is that they don't have control over that slot, so they can't promise that they will actually include the transactions in their allocated slot. So it can like come delayed if like because they have to go through the mempool and the builder might not include them, and maybe the builder will include like the next slots, like opted in validators transaction before like the current random one, like that. So like another approach is like from Justin's like original based rolled up design, where or sequencing a pre-confirmation design, where like you just let the next pre-confirm look ahead handle like the pre-confirmations for like the non-opted in slots. So this way, eventually that entity, that proposer will have their slot and they will have control over it, so they can include it. It seems to give better guarantees. So I was wondering about that part of the design.
That's a great point that I hadn't thought too deeply about. So basically, just to restate what you're saying, if we select a random validator from the pool of validators that have opted in and say, "Hey, you're the one who's doing the next proving block for Keyspace," they may not actually be able to get their proving transaction into a block.
Yeah, exactly.
Yeah, I need to think more about that. That makes a lot of sense. So, what you're suggesting? Go ahead.
Yeah. Hi. Well, there is not too big a difference between what Justin is suggesting and what vanilla-based sequencing is suggesting, because you certainly end up with a scenario where you might not have a single opted-in based sequencer within the look-ahead queue. So you end up with the same things. The good part of what came out of Zuberlim is this L1 Preconfirmations gateway that actually enable you to, despite not being the base sequencer yourself, you can get L1 preconfirmation of the inclusion of this transaction, which is then again even furthermore increase. But yeah, this is the trade-off within any base sequencing when the current L1 proposer has not opted in. Yeah.
So,
and I hope there is not too much static noise around me.
yeah, like, yes, in the case that there's no preconference in the look ahead, yeah, you do have to fall back to some random, but it doesn't have to be random at every slot. That seems pretty.
No. I don't think you understood me correctly. The elected sequencer through the fallback selection can use the L1 preconfirmations infrastructure that is currently being built. I know, for example,
I see.
Header that is header, right? Header that is being built. Sorry, shout out to Drew. Yeah, so Header is currently being built, so you can use that. And now that you have L1 preconfirmations, the cool part is that in this way you can have even more sequencers through vanilla-based sequencing, and you can have even more decentralization because you're having rotation among more actors. Because one of the worst things that, in my opinion, you can do is to give a monopoly over 10, 12 minutes over a single to a single proposer. So in this way, we're actually shuffling monopoly every 12 seconds. I'd argue that this is better in terms of, I guess, many decentralized points.
So is it that there's going to be a separate L1 inclusion preconfer entity that can guarantee the inclusion?
This is what currently is being built in Helder. Again, the scope of L2 and L1 preconfirmations are differing and they are diverging at certain places. Currently, there is L1 preconfirmations gateway being built as a testnet that is going to be, I don't know whether I should be saying this, but expect some exciting stuff on HCC, I guess.
I see. Yeah, even if you have the inclusion, I'm still wondering about the order of these landing, but I guess you can handle that at the contract level.
Yes.
Yeah. Okay, I see.
Yes. The one of the worst parts to be like clear on this one is that it's hard for one to prove who's the current proposer. But yeah, I have written extensively in the white paper on the various ways that you can mitigate this.
Yes.
This downside. I think that is a very simple solution to this, but as our great friend Connor says, we don't like designing systems that depend on several L1 forks. So there are like workarounds that don't require L1 forks, but L1 fork is going to help us tremendously just by telling us who's the current proposer, their BLS public key or whatever it is there, and then base sequencing can be like many crucial points of vanilla-based sequencing and base sequencing can be enforced through Solidity and smart contracts, which is going to be, yeah, very cool.
See, yeah, thanks.
Just to make sure I understood what George is saying, if you have L1 pre-confirmations, then when in the case where you're choosing a random opted-in validator, they know that their transaction is going to get into the block because they have pre-confirmation of it. But what if they try to get a pre-confirmation and they don't get one?
This is the same as submitting this within a block along without pre-confirmation. But then they're paying the inclusion tip. So yeah, I mean, it's the risk of when you're not actually the proposer. There is definitely a risk in any case that is not primary selection. Regardless, there is this risk that is there.
Yeah, it can be the case where like
we can discuss this more on this off-chain in order for me to understand like what's better like what's going to be important for you there in order to be able to advise better on solution, I guess.
Okay, Niran, thank you so much again for this presentation. This concludes the public part of the call.